Hi. So this discussion has to do with rectilinear kinematics with objects that are moving. The objectives are to find some of the quantities like position, displacement, velocity, and acceleration, and we will see some of the relations between position, velocity, and acceleration whenever you have um, acceleration that it's changing or constant. We have to deal with objects in motion, large objects, rockets, airplanes, cars, and they can often be analyzed as if they were particles. So the particle is moving. Why a particle? Well, if we look at this point here or this point on top, it'll all be moving in the same uh, velocity. So we can treat it just as one big particle. Okay? And questions that we'll answer are, for example, if you measure the altitude as a function of time, how can we determine velocity and acceleration? Maybe you can understand this concept better with cars because they're neat as well and we're more familiar with them. So if you have a car moving in a straight line, we can treat this car as a particle, so just as a big particle. So this car started at 0 and it moved a distance s, and it's going at an acceleration that's constant, and that gives it a velocity at different points. So if we have a constant acceleration, that means that here you have a number, and how can we determine its position and velocity at some instance? So that's the question. So let's talk about what's the difference between statics and dynamics. As we mentioned at the beginning of the semester, mechanics is the study of how bodies react to the forces acting on them. We are dealing with statics, so we're looking at the study of bodies in equilibrium. And when we say in equilibrium, meaning that they're not moving or the acceleration is 0 in either way. So acceleration equals 0 means that the velocity equals 0 or the velocity is constant. So that body is in equilibrium, so nothing will shift its position. Now in dynamics, we're concerned with the geometric aspects of motion, and in kinetics, we're concerned with the forces causing that motion. So let's start with the basic principles. First thing, we're going to be dealing in a straight coordinate axis. So in this case, you have this coordinate axis S, meaning this is the distance. And so we have a particle. S is the distance, and let's talk about a distance equal to r that the particle is moving. Okay. So the position of the particle at any instant is given by this vector r. So distance is this magnitude, and r is the vector. Now, whenever we're talking about vectors, remember they have a magnitude and a direction, so that's why we have the position vector r, and this is in bold, so this would be r, or then this distance, which is the scalar amount s in this case. I don't know why they don't call it r like we did before, but anyway, we'll have to deal with it because that's the notation in the textbook. So what we have is that a particle has an initial position that is r. Let's call this just r, and then a final position, and it's it's called prime, r prime, so this would be like r2. So the change in the vector position, or the change in distance, is r prime minus r. If we're in a scalar form, it's s prime minus s would be that distance. difference. Okay, so that's the displacement. So the displacement and distance is the same thing. So the total distance traveled by the particle is the positive scalar amount that represents the total length of the path. So this is important. We'll see some examples in a moment. So we looked at distance and displacement. Now let's talk about velocity, because then the velocity would be the measure of the rate at which that displacement of the particle occurred. Again, the velocity also is a vector quantity because it has magnitude and direction. And in the case of distance, we had meters or feet. And in the case of velocity, we have either the base unit of meters per second or feet per second. Okay, so the average velocity, and this is very important, the average velocity will be, if it's the scalar amount, the change in position over the change in time. So time here, you'll notice that it's not bold, so time is not a vector, but this is a vector, okay? And of course, the average velocity as well. So that is the average. So we're looking at a specific distance over a period of time. But we can check the instantaneous velocity. So this here, the delta, as it becomes small, or you have seen it, that delta as it approaches 0, then instead of delta r, we talk about dr, okay? So it's a very small amount. So what we're looking at as an instantaneous velocity is whenever that interval is infinitesimally small, okay? And then, of course, the instantaneous velocity would be at that specific moment, and then the speed at a certain moment in time is what we call the speed. And the average speed would be like the average velocity, okay? Same thing. Whenever we talk about acceleration, now it's the rate of change in velocity of a particle. So it's also a vector quantity, and let me just write it here. So the change in velocity over a change in time, then it's the acceleration. Now, looking at the dimensional analysis, if we have meters per second and then divided by second, so this is meters second square. So this is what we have, or feet per second square. So same concept where we have, this is the average acceleration, but if we looked at a delta that approaches 0, then instead of delta v, it would be dv. And then instead of a delta t, it's a dt. So then we're looking at the instantaneous acceleration, not just the average, okay? So then we have a derivative. Now, let's take a look at some things here, because this is an important principle. So let me go back just for a minute. So acceleration is dv over dt. And velocity is ds over dt. So if we have here this velocity, remember, if it's the average, would be delta s over delta t, okay? So what we have is, if you have the position expression, like a formula, as a function of time, then ds dt would be the velocity. So if you differentiate the position, you obtain velocity, okay? If you have velocity as a function of time and then differentiate that equation, then the acceleration would be that dv over dt. Again, the average would be a delta v over delta t. So if you differentiate the velocity, then you obtain acceleration, Okay, so if you go backwards, then it's the contrary. So we have, if you have the expression for time, right, ds over dt gives me velocity. Okay, so if you integrate the velocity, so now we have the velocity. So it would be like the first derivative is vt. So then if you go backwards, if I have the velocity and then I integrate, then I get position. Okay, so it goes both ways. So same thing for acceleration. Whenever we said that remember the average acceleration is delta v over delta t, but if you look at the instant is dv dt is the acceleration. So if you have the velocity, the first derivative gives me the acceleration. So if you do the integration of the acceleration, then you get the velocity. So you go backwards. Okay? So in summary, so you have the velocity is the derivative of the position, acceleration is the derivative of the velocity, or you can rearrange this as the acceleration is dv dt. So we can say here acceleration is dv over dt, right? And this here is the change in velocity with time, and then the change in velocity will be ds over dt. Remember, so we're combining those two. So then when you want to integrate, then you get the velocity by integrating the acceleration and the position integrating the velocity, which is what I just said. Okay. The good thing is if you don't understand something, pause it and look at everything. What is important here is that integration represents the initial and the final position of the particle. Okay. So I'm going to show you this reading quiz and you are going to answer. So in dynamics, a particle is assumed to have blank, both translation and rotational motions, only mass, and mass but the size and shape cannot be neglected. No mass or size or shape is just a point. And then the other one would be the average speed is defined as delta r over delta t, delta s over delta t. So read those. We will give you the answer in class. So we'll have a reading quiz when we come back, but now you have time to look at it, okay? I have the answers here. So if you got it right, you'll get it right in class as well. So in dynamics, a particle is assumed only mass. So what's important here is that you do it by elimination. We're going to say that it's a mass. We're really not neglecting the shape, and both here translational or rotational motions, it doesn't always happen. You can have translation or rotational, but not necessarily both. And then the average speed, remember that it's the total displacement over time. Okay. Constant acceleration. So if you have constant acceleration, that means that instead of an equation, you have a number for acceleration. So just as reference, whenever we find the derivative of a constant number is velocity 0. So remember, if I have acceleration and dA dt, and this is a number, this is 0, okay? So you have constant velocity. okay? Or if the dv dt equals 0 acceleration, okay? Constant velocity. So if we have a falling object, then the acceleration would be the acceleration of gravity, which you should know by now. It's 9.81 meters per second square, or 32.2 feet per second square. So if we have constant acceleration, then when you do the integration of a constant number, like this is a number, what you get is t. So you'll have to review some of those expressions. So if I have the integration of t, let me just rewrite this. Well, I will write it here. So dv equals ac dt. So here would be from 0 to v, or let's be 0, and this is from 0 to t. So this would be v minus v0, and this ac goes outside, and then you have dt from 0 to t. So this would be ac t minus 0, v minus v0. So v equals v0 plus act. So that's the derivation of that expression. Okay. So if we have the terms combined with the velocity, then here we have s instead of v0, so this would be one expression. So here we have s ds, so from s0 to s. So this is s minus s0, same thing. So then we have from time 0 to t, okay, now we have v at time t minus v0 if it's a function of the time